Hi everyone, welcome to your last lesson for your first day on exponentials. We ended off the last lesson with a quick word problem. The focus of the rest of this unit is word problems, more specifically, and we're going to break them down a little bit more. So our learning goals: use an equation. So I'm going to give you the equation to model exponential growth and decay. And this is the equation. This is going to make the basis for what we're going to do the rest of our equations off of. So the quote-unquote equation. And there's many different letters. They're just placeholders that you can use. This is just what I want to use. So A equals P, and then in brackets, the number 1 plus or minus R to the exponent T. And now I'm going to write down what each one of those letters stands for, or is a placeholder for. A, we are going to say stands for the final amount. P stands for the principal value in finance, which is coming. But for now, we're just going to call this the starting value. The 1, that's just the number, that's just the number 1. This right here is plus or minus, and you use plus for growth and minus for decay. That makes sense because 1 plus some number will be bigger than 1. And we said exponential growth is for numbers that are bigger than 1. Decay, 1 minus some number, that's going to be less than 1. And we said we use decay for anything between 0 and 1. The R value is your growth or decay rate. And almost always it's going to be given to you as a as a percent. You always need to convert that percent to a decimal to be able to work with it. So as a decimal. And T, or the exponent, whatever it happens to be, just stands for time. Some unit of time. So make sure you have that equation down. We're going to use that to build the rest of our equations. Again, those letters are just placeholders. Really, it could be any letter, but that's the format. 1 plus or minus some value for growth or decay times the initial population, some exponent, usually time, and that's going to give us the final amount. Our first example. At Algonquin Park, a wolf population increased by a factor of 7.8% over a 10-year period beginning in 1997. The initial population was 124. Write a formula to model this. So we're going to stick with our format. A equals. Now P stands for the starting amount. What was the starting amount? Well, it tells us the initial population was 124, and then 1. And is it growing or is it decaying? Is it increasing or decreasing? And it tells us that it's increasing. So plus. And again, common mistake, don't write plus 7.8. It's going to give you a huge number. This is quoted as a percent. We need to convert that to a decimal. And if you have forgotten how to convert that to a decimal, 7.8 divided by 100, 0.078. And then we'll use T for time. So what was the population in 1998? Well, we're not going to plug in 1998 for our exponent. It tells us that it begins in 97. So how many years have passed between 97 and 98? 1. So A equals 124, 1 plus 0.078 to the power of 1. And that gives us 133.7. Now you can't have 0.7 of a wolf, so you are going to round it to the nearest wolf. So this rounds to 134 wolves. What was the population in 2007? Again, we're not plugging in 2007 for our exponent. How many years have passed between 1997 and 2007? The answer is 10. So A equals 124, 1 plus 0.078 to the power of 10. Enter that in your calculator just like you see it. 124 bracket 1 plus 0.078 close bracket exponent button 10. 262.8. We're going to round that to the nearest wolf. 263 wolves. What was the population this year? This year is 2021. So how many years have passed between 1997 and 2021? And if you're not sure, you just do 2021 minus 1997. So our formula, A equals 124, 1 plus 0.078, and then 2021 minus 1997 gives us 24. Enter that into your calculator. Enter that into your calculator just like you see it. 124, open bracket, 1 plus 0.078, close bracket, to the exponent 24. And you should get 752.1, which rounds to 752 wolves. One thing that we didn't do to complete each question that you're going to want to make sure that you do for a test or for your CCA, for any word problem, don't forget therefore statements. So I'm just going to make a note, therefore statements. So don't forget that. We didn't do it here just to save some time, but make sure for a test for any word problem you would write, therefore there's 134 wolves, or therefore there's 263 wolves, and so on. Example number 2. Likewise, at Algonquin Park, the deer population decreased by 3.2% during the same time frame, beginning in 97, and the initial population was 240. So write a formula to model this. So start with A equals, then what comes next is starting amount, 240, number 1, and then is it increasing or decreasing? It says decreased, so that means we're doing minus 3.2. Now don't write 1 minus 3.2. Remember, that's got to be as a decimal. If you have forgotten, divide that by 100, 0.032. And then we'll use T for time. And once you're there, you're all set up, you're ready to go. It's just calculator work. So what was the population in 98? Again, don't put 1998 in for T. It starts in 97. That means 1 year has passed, right? 1998, 97, 1 year. So 1 minus 0.032 to the 1. Enter that into your calculator, and you should get 232.3, which rounding to the nearest deer, 232. As a quick self-check, since we know it's decreasing, if you got a number bigger than 240, you know you've made a mistake with either your formula you set up or with your calculations. So remember, we started at 240. We know we're decreasing. We should definitely get a number less than 240. Doesn't tell us 232 if it's right or not, but we know for sure that it's not wrong, because if we got more than 240, for sure it's wrong. What was the population in 2007? How many years have passed? 10. So A equals 240. 1 minus that, 10 years. Enter that into your calculator. Hopefully you get 173.3. Nearest deer, 173 deer. What was the population this year? So A equals 240, again 1 minus 0.032. And if it starts in 1997 and it's right now 2021, that's 24 years. So 24. And using our calculator, to enter just like you see it, 240 bracket, 1 minus 0.032, close bracket, exponent button, 24, I get 109. Actually, based off rounding, it would actually round up to 110. So 110 deer. Just like last time, I'm going to remind you, don't forget about, if it was a test or an assignment or CCA, don't forget about therefore statements. Hopefully, I'm going to do a bunch of examples. Our third example, hoping to prevent extinction, 75 African bad-eared foxes were moved to an animal reserve in Africa. The fox population increased 15.8% each year, beginning in 1997. So A, write an equation to model this. So A equals our starting population, 75, 1. Does it say increasing or decreasing? It says increased, so that's plus. Again, you can't put 15.8 in. Convert that to a decimal, 0.158, and to the T. How many are there after 5 years? A equals 75, 1 plus 0.158 to the 5, which equals 156.2. Rounding to the nearest 1 would be 156. I'm just going to abbreviate their name, African bad-eared foxes. How many were there at the end of 10 years? Straight up calculator work, 75, using our formula. To the 10, using our calculator, 325.2, which rounds to 325. African bad-eared foxes. And don't forget about therefore statements. Number 4. A cattle farm with a population of 240 cows is declining by 3.4% each year. Again, practice makes perfect. Come up with an equation. A equals starting amount, 240, 1. It says it's declining, so that's minus. Convert that to a decimal, 0.034. Remember, divide by 100 to some exponent. We'll say t for time. What will the expected cattle population be after 5 years? Straight substitution and calculator work. Exponent 5. enter that in your calculator just like you see it, brackets and all. Don't add anything, don't change anything. You should get 201.9, which would round up to 202 cows. So hopefully after doing these 4 examples, it's pretty clear on the process. It's really not that bad. Stick with your base model for your equation, put plus or minus in, convert things to decimals, and it's just calculator work from there. Last example, it's about the trickiest one. This is based off real data. A can of Coke contains 45.6 milligrams of caffeine. Caffeine is eliminated by the body of an average-sized person according to the following table. So the hours it's been in your body and the remaining milligrams. What's the equation? How much caffeine? Blah, 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 blah. So if you're to start up by making your equation, A equals the starting amount, we know that, 45.6. So we know because it told us. We also know at hour 0, it's 45.6. And then 1. And it's saying it's being eliminated in the body, so that means it's decreasing. If you look at your table of values, those numbers are also decreasing, right? 45.6, 39.7, all the way down to 15. So that's going to be minus. But we don't know what the rate is. So we don't know what the rate of decay is. So we're going to have to come up with that. We'll have to recall a previous lesson. How do I come up with the rate or ratio? Wait a minute, there's a word we've done before, ratio. Calculating ratios from a table. So if you remember, bottom up, and we don't subtract. Ratio is a fancy word for divide. Remember exponentials, you're always dividing for this. Bottom up, divide. So 15 divided by 17.2. I get 0.872. 17.2 divided by 19.8. I get 0.869. Next one, 19.8 divided by 22.7. I get 0.872. Next one, 0.869. Now you can keep going just to save time. Those basically are going to keep going all the way up. Now those aren't identical, and they're not going to be for like real world data, right? However, 0.872 and 0.869, those are both really, really close to, so if I only went to 2 decimal places, 0.872 would round to 0.87, and 0.869 would also round to 0.87. So I'm going to say this equals 0.87. Now that just tells me that the body has 87% of the previous amount left. That doesn't tell me what it's decreasing by. So let's think about this. You start off with 100%. You only have 87% left after each time period. So if we did 100%, minus 87%, I'm going to get 13%, which that equals 0.13. And of course, we could have done it with just the decimals, 0.87 and 0.13, those add to 1. So we just calculated our R value, 0.13. Alternatively, so I'm going to write or you could have realized that once you calculate the 0.87, that is your base. We could have gone right to that. Because 1 minus 0.13 is 0.87. Doesn't really matter. Either one. So now that we figured that all out, how much caffeine remains in your body after 12 hours? A equals 45.6, 1 minus 0.13 to the 12. And I get 8.57 milligrams. How much caffeine remains in your body after 24 hours? A equals 45.6, 1 minus 0.13 to the 24. I get 1.61 milligrams. And don't forget therefore statements for a test or CCA. So what that means is if you have a caffeinated Coke, that means even one day after you consumed it, there's still 1.61 milligrams of caffeine remaining in your body. And obviously, if you drink coffee or you drink more pop or anything else that has caffeine in it, there would be even more. So that'd be the trickiest one, getting the information from a table of values, but definitely doable. So that's it for your first word problem lesson. And basically after today, you've pretty much learned all of the necessary material for the unit. So for the rest of the day, you're just working on the workbook, and then you're going to notice in the afternoon for the tutorial period, it's finishing anything you didn't happen to finish. So any lessons, any workbook questions you didn't get done. There is no assignment for this unit. And then tomorrow, you're going to have a very short, really short, probably 10 minutes, final lesson on a couple of specific types of word problems. And then there's going to be 2 review lessons to be done before lunch. And then your test is tomorrow starting at 12:55. So in the afternoon, you are starting your test and you will be done this unit by the end of tomorrow. If you wanted to work ahead, if you get everything done and you want to work ahead just to give yourself a little bit less to do tomorrow morning, then by all means you can work ahead and do any of the video lessons and any of the workbook questions for tomorrow, tonight at some point. So that's it. Have a great rest of your day. Have a great night. And we'll talk again in tomorrow's lessons.